What is Schottky diode? A Schottky diode, also known as a Schottky barrier diode or hot carrier diode, is a type of semiconductor diode that has a unique design and exhibits specific characteristics. It is named after the German physicist Walter H. Schottky, who first described the Schottky barrier phenomenon. Unlike the conventional p-n junction diode, which is formed by joining a p-type semiconductor with an n-type semiconductor, a Schottky diode is formed by the contact between a metal and a semiconductor material, typically n-type silicon. The metal semiconductor junction forms a Schottky barrier, which is a low-resistance, rectifying barrier. Key characteristics and features of Schottky diodes include low forward voltage drop. Schottky diodes have a lower forward voltage drop, typically around 0.2 to 0.5 volts, compared to standard p-n junction diodes, with around 0.6 to 0.7 volts. This lower voltage drop reduces power losses and makes Schottky diodes suitable for high-frequency applications. In a forward-biased diode, the positive voltage is applied to the anode, the p-type region in a p-n junction diode or the metal contact in a Schottky diode, and the negative voltage is applied to the cathode, the n-type region in a p-n junction diode or the semiconductor region in a Schottky diode. This forward biasing reduces the potential barrier at the junction, allowing majority charge carriers, electrons in n-type and holes in p-type, to move across the junction and contribute to the flow of electric current. The forward voltage drop is the voltage across the diode when it is in the conducting state. It is typically measured in volts, V. The value of the forward voltage drop depends on the specific type of diode and its material characteristics. The forward voltage drop for different diodes can vary, but some common ranges are: standard silicon diode, approximately 0.6 to 0.7 volts. Schottky diode, typically between 0.2 to 0.5 volts. Light emitting diode, LED, typically around 1.8 to 3.5 volts, depending on the LED's color and materials. The lower forward voltage drop in diodes like Schottky diodes and certain high-performance p-n junction diodes results in several advantages. Efficiency. Lower forward voltage drop means less power is dissipated as heat in the diode during forward conduction. This increases the overall efficiency of the diode and reduces energy losses. Power loss reduction. The reduced power loss due to lower voltage drop contributes to more energy-efficient electronic circuits and devices. Higher operating speed. Lower forward voltage drop leads to faster turn-on and turn-off times, making diodes like Schottky diodes suitable for high-frequency applications. Lower threshold for operation. Some electronic circuits require low operating voltages, and diodes with low forward voltage drop can be ideal for such applications. Reduced losses in power supplies. In rectifier circuits and power supplies, diodes with low forward voltage drop can minimize power losses, leading to more efficient energy conversion. It's important to consider the specific characteristics of different diodes when designing electronic circuits. Selecting diodes with the appropriate forward voltage drop is crucial to ensure the desired performance and efficiency in the application. Low forward voltage drop is particularly advantageous in high-frequency and power-sensitive circuits where minimizing energy losses and optimizing performance are critical design considerations. Fast switching speed. Due to their low carrier storage time, Schottky diodes have fast switching characteristics. They are widely used in high-frequency rectification and fast switching circuits. In general, fast switching speed means that the device can change its operation state rapidly, typically within nanoseconds to microseconds, depending on the specific component and application. This capability is crucial in various electronic circuits and systems, especially those involved in high-frequency applications and fast digital signal processing. Here are some key points regarding the importance and applications of fast switching speed. Digital logic circuits. In digital electronics, fast switching is essential for creating high-speed logic gates and microprocessors. The ability of transistors to switch rapidly allows for fast data processing and computation. Switching power converters. Power converters, such as buck converters and boost converters, use fast switching transistors to efficiently convert and regulate electrical power. High-frequency applications. In radio frequency (RF) circuits, fast switching components enable the generation, amplification, and modulation of high-frequency signals used in wireless communication systems. Switch mode amplifiers. Fast switching transistors are used in switch mode amplifiers to achieve high efficiency and reduce power losses. Pulse generators and radar systems. In pulse generators and radar systems, fast switching components are crucial for generating and processing short-duration pulses. Data communication. Fast switching devices are used in data communication systems such as fiber optic transceivers to transmit and receive data at high speeds. Fast switching speed is achieved through various techniques and advancements in semiconductor technology, such as smaller gate capacitance. Reducing the size of the gate capacitance in transistors allows for faster charging and discharging of the gate, resulting in faster switching. Advanced semiconductor materials. The use of high-performance semiconductor materials with superior electron mobility can enhance switching speed. Optimized circuit design. Careful design and layout of electronic circuits can minimize parasitic capacitance and inductance, enabling faster switching. High-frequency operation. Devices designed specifically for high-frequency applications are optimized for fast switching. Fast switching speed is a critical factor in modern electronics, where high-speed data processing, communication, and power conversion are essential requirements. As technology continues to advance, researchers and engineers work to develop even faster switching components to meet the demands of ever-increasing data rates and higher frequency applications. Lower reverse recovery time. Schottky diodes have very short reverse recovery times, which means they switch off rapidly when the voltage polarity changes from forward bias to reverse bias. This characteristic makes them ideal for applications where fast turnoff is critical. Lower reverse recovery time is a characteristic of certain diodes, especially fast recovery diodes and Schottky diodes. It refers to the short time it takes for the diode to switch from its conducting state, forward biased, to its non-conducting state, reverse biased, when the polarity of the voltage across the diode changes from forward to reverse. During forward conduction, majority charge carriers, electrons in N-type and holes in P-type, move across the diode junction, allowing current to flow. When the polarity of the voltage reverses, the diode needs to quickly block the current flow to transition into the reverse biased state. The reverse recovery time of a diode is measured from the point where the forward current reduces to zero to the point where the reverse current reaches a specified value, often 10% of the peak reverse current. It is typically expressed in nanoseconds, ns, or microseconds, ms. A shorter reverse recovery time offers several advantages. Switching efficiency. Diodes with lower reverse recovery times switch from the on state to the OFF state more quickly. This reduces power losses and improves the overall efficiency of the electronic circuit. Fast rectification and switching. In rectifier circuits and fast switching applications, a lower reverse recovery time allows for quicker switching, enhancing circuit performance and response time. High-frequency operation. In high-frequency circuits, fast switching is crucial for signal processing and data transmission. Diodes with lower reverse recovery times are well suited for these applications. Reduced switching losses. Faster recovery time reduces the amount of energy lost as heat during the switching process. However, it's essential to consider that not all diodes have a reverse recovery time. In Schottky diodes, for example, the absence of a p-n junction eliminates the reverse recovery effect entirely, leading to virtually zero reverse recovery time. On the other hand, in standard p-n junction diodes, the reverse recovery time can range from several nanoseconds to several microseconds, depending on the specific diode's design and material characteristics. To achieve lower reverse recovery times in diodes, designers employ various techniques, such as optimized junction design. Improving the physical structure of the diode's p-n junction can minimize charge storage and facilitate faster switching. Specialized materials. Using high-performance semiconductor materials with superior carrier mobility can lead to faster switching speeds. Temperature management. Controlling the temperature of the diode during operation can influence its reverse recovery time. Overall, the ability of diodes to quickly switch between conducting and non-conducting states is crucial in many electronic applications, particularly in high-frequency and power-sensitive circuits. Lower reverse recovery times are essential for improving the performance and efficiency of electronic devices and systems. Low junction capacitance is a characteristic of certain semiconductor devices, particularly diodes and transistors, where the capacitance at the p-n junction or the gate channel region is minimized. Capacitance is the ability of a device or structure to store electric charge, and junction capacitance arises at the interface between the p-type and n-type regions in a p-n junction diode or the gate channel region in a field effect transistor, FET. Junction capacitance can have significant effects in electronic circuits, especially at high frequencies, and it is desirable to keep it as low as possible for several reasons. High-frequency performance. In high-frequency circuits, junction capacitance can limit the speed and performance of the device. Low junction capacitance allows for faster switching and signal processing, enabling high-frequency operation. Reduced signal distortion. Junction capacitance can cause signal distortion and reduce the accuracy of signals passing through the device. Minimizing capacitance helps preserve signal integrity. Lower power dissipation. In digital circuits, high junction capacitance can lead to increased power dissipation as the device charges and discharges the capacitance during switching. Lower capacitance reduces power losses. High input impedance. In FETs, low gate channel capacitance results in high input impedance, making the device less sensitive to external noise and more efficient in amplification. Efficiency. Reducing junction capacitance contributes to overall circuit efficiency and reduces power consumption. Techniques used to achieve low junction capacitance in semiconductor devices include thinner junctions. Reducing the physical dimensions of the p-n junction or gate channel region decreases the total charge storage and lowers capacitance. Specialized semiconductor materials. Using high-quality semiconductor materials with specific doping profiles can help reduce junction capacitance. Optimized device design. Careful device design and layout can minimize parasitic capacitance and optimize the electrical characteristics of the device. Low junction capacitance is particularly crucial in high-frequency and high-speed electronic applications, such as radio frequency, RF, circuits, high-speed digital logic, and communication systems. Semiconductor manufacturers continually work to improve device designs and fabrication techniques to achieve lower junction capacitance and enhance the performance of electronic devices. Temperature sensitivity refers to how a device or material's properties and behavior change in response to variations in temperature. It is a crucial consideration in the design, operation, and performance of various electronic components, materials, and systems. Different devices and materials can exhibit temperature sensitivity in various ways. Some key aspects of temperature sensitivity include electrical conductivity. The electrical conductivity of materials can change with temperature. Some materials, like metals, typically have a positive temperature coefficient of resistance, PTC, meaning their resistance increases with temperature. On the other hand, some semiconductors have a negative temperature coefficient of resistance, NTC, meaning their resistance decreases as temperature rises. Semiconductor properties. The performance of semiconductor devices, such as diodes, transistors, and integrated circuits, can be affected by temperature variations. Temperature sensitivity can influence parameters like forward voltage drop, leakage currents, and switching characteristics. Thermal expansion. Materials, especially metals, expand or contract with changes in temperature. This thermal expansion can cause stress and mechanical deformation in devices and structures. Thermal noise. Temperature can influence the level of thermal noise in electronic circuits, affecting the accuracy and performance of sensors and communication systems. Temperature compensation. Some devices and circuits require temperature compensation to maintain stable performance across a wide temperature range. This compensation may involve using specialized components or incorporating temperature sensing and feedback mechanisms. Sensitivity of sensors. Many sensors, such as temperature sensors, pressure sensors, and humidity sensors, rely on temperature-sensitive materials or components to provide accurate measurements. Battery performance. The capacity and performance of batteries can vary with temperature. Cold temperatures can reduce battery efficiency, while high temperatures can accelerate battery aging and decrease overall lifespan. Manufacturers and designers consider temperature sensitivity in their products and systems to ensure reliable operation and consistent performance over a range of temperatures. Strategies for dealing with temperature sensitivity include temperature compensation circuits, implementing compensation circuits that adjust for the effects of temperature on device parameters, maintaining stable operation. Thermal management, using heat sinks, cooling systems, and proper ventilation to regulate and control the temperature of electronic components. Selection of materials, choosing materials with specific temperature characteristics to suit the intended application and environment. Calibration, calibrating sensors and instruments to account for temperature-induced variations in their measurements. Operating range, specifying the temperature operating range of devices to ensure they are used within their design temperature limits. Temperature sensitivity is a critical consideration in various industries, including electronics, aerospace, automotive, medical, and many others. By understanding and managing temperature effects, engineers can design robust and reliable systems that perform optimally under a wide range of operating conditions. Power rectifiers. Power rectifiers are electronic devices used to convert alternating current, AC, into direct current, DC. They are essential components in power supply circuits, where they rectify the incoming AC voltage to provide a steady and regulated DC output. Power rectifiers play a crucial role in a wide range of applications, from small electronic devices to large-scale industrial systems. The primary function of power rectifiers is to allow current flow in one direction while blocking it in the opposite direction. They achieve this through the use of semiconductor diodes, which are the most common type of power rectifiers. Semiconductor diodes, like PN junction diodes or Schottky diodes, have the property of being rectifying devices, meaning they permit current flow in the forward direction, from the anode to the cathode, and block it in the reverse direction. There are two main types of power rectifiers. Half-wave rectifiers. In a half-wave rectifier, only one half of the AC input waveform is converted to DC. It uses a single diode to conduct during the positive half cycle of the AC voltage, allowing current flow to the load, while during the negative half cycle, the diode blocks current flow. Full-wave rectifiers. Full-wave rectifiers use four diodes arranged in a bridge configuration, known as a bridge rectifier, to convert both the positive and negative halves of the AC waveform into DC. This results in a more continuous and smoother DC output compared to half-wave rectifiers. Power rectifiers are available in various configurations and power ratings to suit different applications. Some common types of power rectifiers include standard silicon diodes. These are the most widely used power rectifiers, providing a low-cost solution for many applications. Schottky diodes. Schottky diodes are used in high-frequency applications and situations where fast switching is required due to their low forward voltage drop and fast reverse recovery time. Fast recovery diodes. These diodes are designed to have a reduced reverse recovery time, making them suitable for high-frequency and fast switching applications. Ultra-fast rectifiers. These diodes have even faster reverse recovery times and are used in applications where very high switching speeds are required. Silicon carbide (SiC) diodes. SiC diodes offer higher efficiency and temperature performance, making them suitable for high power and high temperature applications. Power rectifiers find applications in various electronic devices and systems, including power supplies, battery chargers, motor drives, inverters, and rectifiers for electrical grids. They are essential components for converting and regulating electrical power in a wide range of industries, from consumer electronics to industrial automation and renewable energy systems. Switching circuits, also known as digital circuits or digital logic circuits, are electronic circuits that are designed to perform digital switching operations. They process binary signals, zeros and ones, and are fundamental building blocks of digital electronics, forming the backbone of modern computing and electronic systems. Switching circuits use digital logic gates to perform various logical operations on input signals and produce output signals based on the logic implemented. The primary components of switching circuits are digital logic gates, which are electronic devices that perform logical operations on binary inputs and produce binary outputs. The common types of logic gates include AND gates, OR gates, NOT gates, also called inverters, NAND gates, NOR gates, and XOR gates. By connecting these gates together in various configurations, complex logical operations can be performed. Some key characteristics and features of switching circuits are: digital signals. Switching circuits process digital signals that have two discrete levels: logic 0, low voltage level, and logic 1, high voltage level. These binary signals represent the basic units of information in digital systems. Boolean algebra. The behavior of switching circuits is based on Boolean algebra, a mathematical system that represents logical operations using algebraic expressions. Boolean algebra provides the foundation for designing and analyzing digital logic circuits. Combinational and sequential logic. Switching circuits can be classified into combinational logic and sequential logic circuits. Combinational logic circuits generate outputs solely based on the current inputs, while sequential logic circuits have outputs that depend not only on the current inputs but also on the past inputs and the circuit's internal state. Truth tables. Truth tables are used to describe the operation of switching circuits, showing all possible input combinations and their corresponding output values. Logic families. Switching circuits can be implemented using various logic families such as TTL, transistor-transistor logic, CMOS, complementary metal oxide semiconductor, ECL, emitter-coupled logic, and more, each with different characteristics in terms of speed, power consumption, and voltage levels. Switching circuits are used in a wide range of applications, including but not limited to digital computers. Switching circuits are the foundation of digital computers, where they perform arithmetic, logic, and control operations in microprocessors and CPUs. Memory devices. They are used in memory units such as RAM, random access memory, and ROM, read-only memory, to store and retrieve data. Control systems. Switching circuits are used in control systems to process input signals and generate appropriate control signals for various devices and processes. Communication systems. They are used in communication circuits, such as data transmission and reception in digital communication networks. Digital displays. Switching circuits control the operation of digital displays, such as LED displays and LCDs. Switching circuits play a critical role in modern electronics and information processing. The ability to process digital signals efficiently and accurately has revolutionized various industries, making digital systems an integral part of our daily lives. Voltage clamping and protection. Voltage clamping and protection are techniques used to limit or control the voltage level in electronic circuits, preventing voltage spikes or overvoltage conditions that could potentially damage components or disrupt the normal operation of the circuit. These techniques are commonly employed in a wide range of applications to safeguard electronic devices and ensure their reliable performance. 1. Voltage clamping. Voltage clamping is a method used to limit the voltage across a particular component or circuit to a predefined level, often referred to as the clamping voltage. It is typically achieved using specialized electronic devices known as voltage clamps or voltage limiters. The primary purpose of voltage clamping is to protect sensitive components from excessive voltage levels. When the voltage across the clamped component reaches the clamping voltage threshold, the clamping device activates and conducts, effectively limiting the voltage to the predetermined value. This prevents any further increase in voltage beyond the clamping level, protecting downstream components from potential damage due to overvoltage conditions. Voltage clamping is commonly used in various applications, including transient voltage suppression, TVS diodes. TVS diodes are a type of voltage clamping device used to protect electronic circuits from transient voltage spikes, such as electrostatic discharge (ESD), and voltage transients due to lightning or other disturbances. Zener diodes. Zener diodes can be used as voltage clamps by selecting a Zener diode with a breakdown voltage close to the desired clamping voltage. When the voltage exceeds the Zener's breakdown voltage, it starts conducting and limits the voltage across the circuit. Crowbar circuit. A crowbar circuit is a voltage clamping circuit that provides a low resistance path to ground when a voltage threshold is exceeded, effectively clamping the voltage to a safe level. 2. Voltage protection. Voltage protection refers to a set of measures and devices used to safeguard electronic components and circuits from potential damage caused by excessive voltages or voltage spikes. Some common voltage protection techniques include fuse protection. Fuses are sacrificial devices designed to break the circuit when the current exceeds a safe threshold, protecting components from overcurrent and overvoltage conditions. Circuit breakers. Similar to fuses, circuit breakers are devices that automatically open the circuit when an overcurrent or overvoltage condition is detected. Surge protectors. Surge protectors are devices designed to divert excessive voltage spikes to the ground, protecting connected devices from voltage surges due to lightning or other sources. Overvoltage protection ICs. Integrated circuits designed for overvoltage protection can be used to monitor the voltage levels and activate protective measures when the voltage exceeds safe limits. Voltage regulators. Voltage regulators are used to maintain a stable output voltage, protecting downstream components from voltage fluctuations. Voltage clamping and protection are essential considerations in electronic circuit design, especially in systems that are exposed to unpredictable or high-voltage environments. By implementing effective voltage clamping and protection measures, designers can enhance the reliability and longevity of electronic devices and ensure safe operation under various operating conditions. Mixers and detectors are essential components in electronic communication systems, particularly in radio frequency, RF, and microwave applications. They play crucial roles in signal processing, frequency conversion, and modulation-demodulation processes. Let's take a closer look at each of them. 1. Mixers. Mixers, also known as frequency mixers or frequency converters, are electronic devices used to combine two or more input signals at different frequencies and produce an output signal that contains various frequency components, including the sum and difference frequencies of the inputs. The main function of mixers is frequency conversion, which is a fundamental operation in RF and microwave systems. They are commonly used in frequency translation. In RF communication systems, mixers are used to convert high-frequency signals to lower intermediate frequencies, for further processing and amplification. Upconversion and downconversion. In wireless transmitters and receivers, mixers are used to upconvert baseband signals to RF frequencies for transmission and downconvert received RF signals to baseband frequencies for demodulation. Frequency generation. Mixers are used to generate new frequencies by mixing an input signal with a local oscillator, LO, signal. Phase lock loops. PLLs. Mixers are employed in PLL circuits to compare the phase and frequency of a reference signal with a feedback signal, allowing precise frequency synthesis and clock synchronization. Heterodyne receivers. Mixers are essential components in heterodyne receivers, where they mix the incoming RF signal with the LO signal to convert it to a lower if for further signal processing. 2. Detectors. Detectors, also known as demodulators, are devices used to recover the original information or baseband signal from a modulated carrier signal. They are used in communication systems to demodulate signals and extract the transmitted information. There are different types of detectors, depending on the modulation scheme used in the communication system. Envelope detectors, used for amplitude modulation, AM, signals. Envelope detectors extract the envelope, amplitude variations, of the modulated carrier to recover the original baseband signal. Synchronous detectors, also known as synchronous demodulators, they are used for phase modulation, PM, and frequency modulation, FM, signals. Synchronous detectors compare the received modulated signal with a reference carrier to recover the original baseband signal. Coherent detectors are used for phase shift keying, PSK, and quadrature amplitude modulation, QAM, signals. They employ a coherent reference signal to demodulate the incoming signal accurately. Detectors are critical in demodulating modulated signals, allowing the receiver to extract the transmitted information from the carrier signal accurately. Both mixers and detectors are essential components in modern communication systems, enabling efficient signal processing, frequency conversion, and information extraction. They are widely used in various applications, including wireless communication, radar systems, satellite communication, and many other RF and microwave systems. Photovoltaic solar cells. Photovoltaic (PV) solar cells, also known as solar photovoltaic cells or solar panels, are semiconductor devices that convert sunlight directly into electrical energy through the photovoltaic effect. They are the basic building blocks of solar photovoltaic systems and play a key role in harnessing solar energy for various applications, from small-scale residential installations to large-scale solar power plants. The photovoltaic effect, first discovered in 1839 by French physicist Alexandre Edmond Becquerel, refers to the generation of an electric current when certain materials are exposed to light. In solar cells, this effect occurs when photons, particles of light, strike the surface of the semiconductor material, exciting electrons and creating electron-hole pairs. The semiconductor's built-in electric field then separates these electron-hole pairs, causing electrons to flow in one direction, creating an electric current. Here are some key features and components of photovoltaic solar cells. 1. Semiconductor material. Solar cells are typically made of semiconductor materials such as silicon, crystalline or amorphous, gallium arsenide, cadmium telluride, or copper indium gallium selenide. Silicon-based solar cells are the most widely used due to their abundance, efficiency, and stability. 2. P-N junction. Most solar cells have a P-N junction, which is a region where the P-type semiconductor, with positive charge carriers, and the N-type semiconductor, with negative charge carriers, meet. This junction plays a crucial role in the separation and flow of charge carriers during the photovoltaic process. 3. Solar cell efficiency. The efficiency of a solar cell refers to the percentage of sunlight energy that the cell can convert into electrical energy. Efficiency varies depending on the type and quality of the semiconductor material, with commercially available solar cells having efficiencies ranging from around 15% to over 20%. 4. Solar panel. Solar cells are connected in series in parallel configurations to form solar panels or modules. Solar panels are the units commonly seen on rooftops and in solar farms. They provide a higher power output and voltage compared to individual solar cells. 5. Applications. Solar cells and panels are widely used to generate electricity in various applications, including residential solar power systems, commercial and industrial solar installations, off-grid power systems, portable solar chargers, and utility-scale solar power plants. 6. Environmental benefits. Solar cells are a clean and renewable energy source, producing electricity without emitting greenhouse gases or air pollutants. They contribute to reducing carbon emissions and mitigating the impact of climate change. 7. Cost and advancements. The cost of solar cells and panels has been decreasing over the years, making solar energy more accessible and economically viable. Ongoing research and technological advancements aim to improve solar cell efficiency, reduce costs further, and enhance the overall performance of solar photovoltaic systems. Photovoltaic solar cells have transformed the energy landscape by providing a sustainable and environmentally friendly alternative to conventional fossil fuel-based electricity generation. As solar technology continues to evolve, it holds great promise for the future of clean and renewable energy production. Overall, Schottky diodes offer unique advantages in specific applications, particularly where fast switching, low power losses, and high-frequency operation are crucial design requirements. This is all about Schottky diode. Please subscribe if you like the video. Thanks for watching.